So now we've been able to add one more kind of instruction to our family of instructions that we've seen, IO, gen, and now parser. So a parser for an A is an instruction for parsing an A, may or may not fail, and it's run by using the function parse. And there's some more examples of, I don't know exactly what that does, but anyway, something of that type. So in summary then, there's different kinds of instructions, and each of them has a notion of what it means to run an instruction. Now that's not necessarily the case for all parsers, but it is for all monads, but it is for these three in particular. And you notice that this is just a function from the library. You can run quick check parsers. Well, quick check does it. You can also use the sample function. And in this one, they run automatically. So just a bit of terminology that you'll come across when you look at things relating to monads. So sometimes people refer to a monadic value, and that's a value, for example, an IO of string is a monadic value, whereas a string is just an ordinary value. An IO of string is a monadic value. It just means an expression whose type is an instance of the class monad, like IO or gen or parser. So when we say T is a monad, T might be IO or gen or parser. We just mean that T is an instance of the class monad. It's a member of the class. And that's why we can use do notation, because anything in the class can use do notation. And in the course, we've often referred to monadic values as instructions. And it's important to understand that that's not standard terminology. That's just something that we've been using. But sometimes they're called actions rather than instructions. And that's what you'll see probably in the Learn Your Haskell book. So what is really inside a monad? To be an instance of a class, you have to have certain functions or definitions. So examples that we've seen is the arbitrary class. So to be a member of the arbitrary class, you need a function called arbitrary. To be in the EQ class, you need the equality operation to be defined. To be in the show class, you need the show function to be defined. And monad is not different in this regard. There is a certain minimum number of functions that you have to define for a type to become a member of the monad class, to be an instance of the monad class. And more specifically, the function you need, the important function, is this guy here, which is referred to as bind operation. So if we view of M of A of instructions for producing an A, it's a way of combining instructions for producing an A with a function that takes an A and gives the instructions for producing a B, and sort of finds a way of plugging these together, even though they don't match. The type of this doesn't match the argument for this function, but the bind operation finds a way of doing that gives you a way of plugging these things together in order to end up with instructions for producing a B. So that's the core operation. And there's also, of course, the return operation, which takes an A and turns it into an M of A. So return of 2 could be something in the monad for the IO monad. It's an instruction that doesn't do any interaction with the operating system, returns the value 2. But it could also be viewed as a random generator, which always generates the number 2. It can also be viewed as a parser, which always succeeds and returns you the value 2 without actually even bothering to look at the input string. The inequality function is just defined as the negation of what you get from the equality function. So you don't need to define that. That has a default definition. Now actually I'm bending the truth a little bit. I'm saying that this is what a monad is. It's really these two functions, these two things. But actually that's a bit old school because there have been changes in Haskell fairly recently, in the last few years. So monad is actually a subclass of another class called applicative, which is in turn another subclass of something called functor. So a monad is an applicative, and an applicative is a functor. I don't really want to get into applicatives and functors, but fortunately, those things are covered very in a detailed way in the Learn Your Haskell book. I'm just going to focus on monad, and I'm going to kind of take some shortcuts so that I can define monads without having to think about applicatives and functors. But in actual fact, strictly speaking, the only thing you need to be in a monad, once you're already in functor and applicative, is this guy. And I'm going to do it the old-fashioned way and define it with this guy and the return function, and the rest can be done automatically. And if you actually want to know what that automatic nonsense is, I just put this in my parsing library. Whatever monad you're defining, I just cut and paste this in and didn't have to worry about functor and applicative. And that's really just because I don't want to get into the details of those in this lecture. So you don't need to understand this if you want to just understand the monad part. Okay, so before we can talk about the parser monad, I want to talk about do notation in general. And in fact, do notation is really just a shorthand for using the functions that every monad has. And that's the bind function, in fact, and the return function, in fact. But the bind is the key here. So these are small examples. If you just had a do monad that involved just performing two actions, then in fact that translates to just the application of this operator with the first action followed by the second action. And that in turn is just defined by using the bind operation with this. I don't care what the argument is. I don't care what value I get from the first action. I'm then going to perform the second action. So this is when you perform one action followed by another, and that's something typical maybe in the IO monad, print something on the screen, read something from a file, then that really just translates to the application of functions from the monad class. In the case when we perform an action and then give a name to the result that we get, for example, this might be reading from a file and this might be the contents of the file. That just translates to taking the first action and feeding the result you get into this function, the function which when you give it a v does these things here. So Act 2 can use the value v because that's part of the function, and that's exactly what you do in the do notation. Act 2 will use whatever value is named here. So if we take a concrete example of this, let's take a monad example. Let's take an example of this from the IO monad, where we get a file name by reading it from a line. So I type a file name in, and then it will actually read the file that corresponds to that, and then we'll call the contents. And then it will print out the first 10 lines at most. If there are 10 lines, it'll print out as many as it can otherwise, of the contents. Oh, sorry, the first 10 characters, not the first 10 lines. So this is just one string. Okay, so that's what the do notation is. But what we've just learned is that do notation is just a shorthand for something else. And in fact, this is the slightly more general case. If you have some action and then some other actions below it, then that translates to this thing here. So this thing here is the same as perform the first action, take the first action, that's get line, and feed the result of that action into the function. It will give a file name. We take the file name and then we do the rest. And what is the rest? That's these two lines here. So it's get line, and the result of get line is fed using the bind operation into this function. So then we can apply the translation as defined up here once more to this expression here. And what do we get? Well, what we're doing is read file of that file name. So that's the next thing, the next action. And the result of that is going to be fed into whatever comes next. What do we do with the next thing? Well, we take the contents and then we put string. And we could put a do in front of that, of course, but in fact, putting a do in front of a single action is unnecessary. In fact, we can simplify this even further if we use the fact that we have higher order functions, because we can actually turn this into one long pipeline of composed higher order functions. So we could take this bit here and just view that as a read file. And this thing here is a composition of two functions. It's the composition of the take10 function and the putstra function. So that could also be written actually without any mention of the names. So what we listed here is the full translation, or at least part 1. Whenever you have a sequence of actions, you can peel off the first action and then it pipes into the rest using this double arrow, which is actually just a simplified form. And when we have an action giving us a value, then that's translated into the action followed by a function which takes that value as an argument and then does the rest of the actions. And when you finally get down to a single action, do of a single action is just the same as that action. Now that's actually not all the cases of the do notation. There are a couple of other cases, and for completeness we'll look at them here. So one is that there is a notion of a let binding you can have. When you have something which is not monadic, you want to name something inside a do, then that just translates to a let expression in the standard way. Perhaps a little bit more complicated is if you have a pattern matching inside a do. Now, pattern matching is something that might fail. So what happens when it fails? How does it handle that? Well, actually, there is a standard error function which actually will give an error in the default definition. So basically, it will take this first action, and feed it into the function f, where f, if it gets something of the right pattern, will carry on, but if it gets something which doesn't match the pattern, then it will give this error message. You can, of course, override this. If your particular monad doesn't want to give an error message, wants to do something else, then you might not have an error message. But in many of the cases we've seen, this will just give an error message. Okay, so we can get some more intuition about monads with some nice examples that I've taken from a blog post, and they look very similar. The illustrations look very similar to the Learn You a Haskell illustrations, but actually they're from a different author. But they're very nice. So we're going to use the example of the maybe monad. So maybe is also a monad, and it has many of the characteristics you'll recognize. You can kind of think of the monads we've seen as producing values that are wrapped in some kind of context. So, for example, read file produces a string, but it's wrapped in the I/O context, a kind of I/O bubble that you can't get out of. A gen of a string would be a random string, so it's kind of a string that's wrapped in a sort of randomization context, which is not the same as just a string. And a maybe is also a monad. It produces a value in a context where the value might be the just, which is where you actually have a value, or a nothing, where the kind of context doesn't contain anything. So in these nice pictures, we have a value inside a box here for the just, and this sort of empty box representing the nothing. So we think of this as the context for the value. Okay, so let's take a step back. Let's visualize a function, and this is not quite the way I was visualizing it with right to left boxes. This is from top to bottom. This is the -1 function, subtract 1 function. You feed in a value at the top, and it spits out a value at the bottom. Okay, and what's nice about that is we can compose functions. So when we compose functions using the dot, what that just means is plugging them together. That means we feed into the innermost one, the rightmost one, and then the output of that then gets fed into the next one. So if we have the +2 function and the +3 function, we feed in 10, we'll get out 15. So here's a different function. It's a function that gives us a maybe. It halves a number, but only succeeds. It only gives you a just of something if the number is even. So you can halve an even number. When you try and halve an odd number, you get nothing. Okay? So for the sake of argument, this is just the function we're going to use for examples. So this function drawn in the same way, put in a value, and it returns a wrapped value. And that wrapped value is either in the just, a value in a box just, or it's an empty box, the nothing. Now the thing is that if we wanted to take a wrapped value and feed it into a function like half, it wouldn't work. They don't fit. The types don't fit. Here, half is expecting a number to go in. So we can't compose half with itself, for example, because the types of things coming out of half don't match the type of things going into half. So we can't halve things twice using function composition. Now one way to think of this bind operation of the monad is a way to make these things fit together. It's the thing that shoves the wrapped value into a function that is not expecting a wrapped value. So here's some exact examples using the maybe monad, and you'll soon get an idea for what this function does. If we wanted to feed the value, this wrapped value into the half function, then we can do it using this guy, because half normally takes just a number, but now we can feed it with a maybe number. And if we feed it with this particular maybe number, we'll get nothing. If we feed it with this maybe number, just 4, we will get just 2. So what this thing is actually doing is sort of unwrapping the value, feeding it to the function, and producing the output. And if we actually put nothing in, as in this case, then we'll get nothing out. So if we feed nothing into the half function, we get nothing else. So monad is one of our instances of, maybe is one of the instances of monad because it has this function. And you can see what this function does from these examples. But we'll give the definition in a moment. So the bind operation can be thought of as this thing that allows us to feed a monadic value into a function that's not expecting a monadic value. It takes a monad, for example, like just 3 is a monadic value, and a function that returns a monad, like the half function returns a maybe int, and enables you to apply this function to the value that is inside this monad. That's what this guy is doing. So let's take the example for that. What this operation does, what the plunger operation does, is that it unwraps the value, gets the value out, feeds the value into the function, and and you get a wrapped value out again. And for this particular monad, if you have nothing going in, then nothing can be done, so nothing comes out. So this is feeding the nothing value using this function into this guy. So let's take a slightly longer example, this chain of function applications, and these associate to the right. So we're taking this value and feeding it into this function. So this is just basically pushing this in through a whole chain of halves. Okay. So what does this operation do? Well, if we start with the just 20, there it is, 20 in a box. This operation will unwrap it and feed it into the function, the half function. And what that half function will produce, in this case, is the wrapped 10. So we take the output of that function and feed it into this guy, this thing here. So how does that work? Well, how does this guy work? It works in the same way. It unwraps, feeds it into the next function, which gives us a wrapped 5, and then we take that and this final plunger here, we unwrap the 5, feed it into the half function, and let's see if I can find the final slide. There it is. We take the 5, feed it into the very final one, and outputs nothing, sadly. So maybe is a monad, but it's a very simple one. If you have a function and you're feeding it with a maybe value, the way it does it is, if you have a just, then that's no problem. You unwrap the value from the just and feed it to the function. You apply the function k to x. But if you have nothing, you try and feed nothing to whatever function you have, well, then the result will be nothing. And the return operation, that's just the just operation. And it turns out this is an example where actually the fail operation is also nothing, but this is not going to be terribly relevant for today. So we don't actually give an error when we fail in the maybe monad, we give nothing instead. Now this looks super simple. It looks something that's not going to be terribly useful. But it actually turns out to be pretty useful in practice. It saves us from a lot of code spaghetti. So let me give an example of that. So imagine we have congestion charge billing. So the situation is that when a car drives through, the registration number is registered, and some database helps us look up car owners in the database, and once we know who the car owner is, we can look up where they live in order to send them the bill for for passing the road toll. So we're going to model this in a simple but not totally ridiculous way with the following tables. And we're using the simple notion of tables here, but it doesn't actually matter. We could actually use fancy tables using the functions we had in the previous lecture. So to find the registration, to find the owner of a given car registration number, we have a car register. It's a table that lets us look up, given a registration number, a personal number. And a personal number is used to find the name of the owner using a name register. So if you have a personal number, you can look up what's the name of the person. And then we also have an address register. If you have a name, then you can look up their address. Actually, maybe it should be name and personal number, allows you to look up an address. Maybe that would be more realistic. Okay, so let's look at some examples. So we've all of these, just to view all of these things as strings: registration numbers, personal numbers, names, addresses. They're just all strings. Not too important. So here's an example of a almost complete car register. I just didn't bother typing the rest. So this is not Haskell, this bit here, but the rest is Haskell. So here's a personal registration number, and here's a personal number that corresponds to. And here's a possible name register entry. This personal number, that's Dave. And the address register, oh yeah, that's more like what I thought, it's more realistic. If you have both a name and a personal number, you can find an address. So if you have Dave and this personal number, you can find out where Dave lives, and you can then send him your bill. So here's a function using lookup, which is how we look up names in tables. If you want to look up an A in a table, you get a maybe B because it might not be in there. So I'm going to define a function here, billing address, which takes a car registration number and maybe gives us a name and address. So in order to do this, we have to go through a chain of lookups. The first lookup we do is look up the car in the car register. If it gives us nothing, well, there's nothing we can do. If we find a personal number, we get a just personal number, then we can look up the personal number in the name register. So we do another case expression after we've looked up the personal number in the name register. If that gives us nothing, then we still can't get an address. But if we get a name, so what have we got so far? We've got a personal number and a name. If we've got a personal number and a name, we can look up in the address register that name and personal number to finally get the billing address. If, despite everything, the name and the personal number is not in the address register, we get nothing. But otherwise, if we get an address, then what we return is the name and the address as a pair in the type maybe name address. So there's the code for doing something relatively simple. But you see what kind of spaghetti we get here. Because we have to do a sequence of lookups, and we have to take into account every possible case. Now, maybe is a monad. And so because it's a monad, we can use do notation to define functions that work with the maybe type. And in this particular case, the do notation actually tidies things up dramatically. Here's how we can rewrite this using do notation. So remember now that lookup is something that returns something of type maybe. So maybe is in the monad. So that means we can get a personal number from the maybe type. Now this might fail, which means the whole thing gives us nothing. But that's not a problem. That's exactly what we want. If this fails, then we get nothing. So what this says is look up the car to maybe get a value, and let's call the value personal number. Look up the personal number in the name register, call that the name. And now we finally look up the name and the personal number in the address register to get the address, and then we can return the name and the address. Remember, return is just the same as just. So the result is a just. So this might look very mysterious, but actually we can now undo the do notation because we know that the do notation is just a shorthand for using the bind operation. So we can do that, and if we do one step of that undoing, we see that what this billing address of car is equal to is you first look up the car in the car register and then feed that maybe value into this function. And so that's what the bind operation allows us to do. This is a function expecting a personal number. So what this feed operation does will unwrap the personal number if we have one. But if we have nothing, then the whole thing will give us nothing. So before we can summarize the whole thing, we need to go back to our parser and see how we can write our parsing library.